uh, stardust that brought back samples of the dust that comes off of a comet and of interstellar particles that are zooming through the solar system. Then Osiris-Rex is only the 4th sample return mission from NASA. Sample return is difficult. You have to bring it back to Earth, but it provides us with such opportunities to study those samples with machines, with instrumentation that you cannot put on a spacecraft. So it's a gift that keeps on giving, because those samples will be studied by generations of future scientists. And so, yes, it's very important. We've been busy. I've been blessed to have my career doing what I consider the golden age of planetary exploration. So we've had a number of missions, and there are many more in the planning stages. And I've had the tremendous privilege to work with the Osiris-Rex team on this. And it's been very rewarding and in some ways surprising. And we can be discussing that as we show some of the images.
Absolutely. Okay. Well, excellent. I wanted to show everyone and talk about the whole, beginning of this, and I'll have you speak to the history, getting up to launch day. But the launch itself, I felt very fortunate that I was able to attend, and it was a pretty big deal. Bill Nye was there. It was this festival type atmosphere. You had all kinds of, there were just thousands of people watching. But can you talk a little bit about you're behind the scenes, you're, in the trenches. Can you talk a little bit about what it felt like on launch day?
Oh, it was hard to describe, but we were all so excited and nervous, because the typical, this was in September of 2016, and the typical weather at that time of year is either a thunderstorm, a tropical storm, or even a hurricane. And we had absolutely perfect weather. The wind was onshore. The skies were completely clear, as you can see in these images. And we had a perfect launch. It went right on time. There were no delays. And so thanks to the ULA for the launch vehicle, thanks to the Kennedy Space Center for the wonderful support that they gave us. And the team was all assembled. We had a kind of a preliminary preparation dinner the night before, and then we were all together out there at the Cape, probably in a different site from yours, Justin, and there was electricity, right? And we were just all, and in any case, I was there with colleagues, friends, all of us on the team, and I was taking a video of the launch. And then that night I spent with friends that live in Satellite Beach, and they said, "Did you post this?" I said, "No." "Why?" "I never post anything." "Oh, we'll show you how to do that." So they showed me how to post it on Facebook. And I was getting all these responses, and people were saying, "I don't know what I'm more surprised with, that they launched the spacecraft successfully, or that Humberto is posting on Facebook."
Not something that you're known for, right?
Nope.
But you got a pretty good, pretty good video of it. How far away were you guys? Probably maybe 3 or 4 miles from the launch pad?
We were about 2 miles from that.
Oh, wow.
We were right there. We were wherever that scene was taken from.
Oh, excellent.
Yes.
Yeah, it was a perfect day. We were at the visitor center, and they had set up all kinds of bleachers and giant screen televisions, and just interviews and things like that leading up to the launch. And then, of course, it cut over to launch, and just within seconds of it passing the tree line, we were able to see it go up. So
yeah, and one of the things that has always struck me with every launch is that you see it go up, and it's only a few seconds later that you start to hear the rumble. Right?
Yes.
And it reminds you that light travels a lot faster than sound.
Oh, absolutely. Well, let's talk a little bit about its target mission. So we're talking about an asteroid named Bennu. And can you kind of speak to, all the asteroids that are out there, orbiting the sun? What really stood out for Bennu as
As the
destination.
target, yes.
Yeah.
There are many asteroids, lots of asteroids between Mars and Jupiter, of course, in the asteroid belt, and there are many near-Earth asteroids. And Bennu was selected for two main reasons. Number one, it is the most potentially hazardous asteroid, or it was at the time that when we selected it as our target. And by that, I mean that Bennu is not threatening Earth with an impact right now, but it could, if its orbit were to evolve in a specific way, it could threaten Earth in about 160 years. So if Bennu is going to threaten Earth and needs to be deflected, we wanted to go to it and understand it as well as possible, so that if we had to deflect it, we would know how to do it. The other reason why I got selected is because Bennu is one of those asteroids that is primitive, and by primitive we mean it has not changed very much since the time it formed, and it contains elements in it and molecules that we still have a very strong interest in. In other words, Bennu and other primitive asteroids contain primitive organic molecules, carbon chains with hydrogens and nitrogens and other components that are the types of building blocks that were present on Earth before life formed. However, on Earth, we cannot tell what was present before life formed, because life itself transforms completely its environment and erases any record of what came before. So by studying Bennu and bringing back those samples and studying those organic molecules that existed on Earth before life formed, we may be able to tell how life formed and on Earth, and how it may have formed elsewhere, like on Mars, on the moons of Jupiter, or even on planets around other stars. So understanding this very important step from a complex organic molecule that is not live to the first cell, it's a step that is crucial for us to understanding the origin of life, and we still don't know what that step was. So Bennu may help us understand that. And of course, if there was a practical side of mitigating the threat of Bennu if it were to threaten Earth in the future. And the third component of this, or third and fourth, but third component of this, which was not talked about very much back then, but it's much more discussed now, is that Bennu can provide us with quite a bit of resources if we decide to mine it. And in case of mining asteroids, the most precious component would be water. So Bennu is very rich in organic minerals, and if we were to go to it and extract the water from those organic minerals, we have a great base of customers that would want that water. And that's everybody who has an Earth orbiting satellite. If you can buy fuel made of oxygen and hydrogen, which you can produce by dissociating the water molecule, you then have fuel that you could sell to the people who are operating these Earth orbiting satellites, be them communications or other types of satellites. And so even though new technology, for example, by SpaceX, is lowering the cost of launch vehicles, the cost of putting something in space is still high. And so what sits on the pad is only about 1% or less of that makes it to orbit. So the moment that we could mine asteroids and produce water for less than it takes to launch it, we're going to have a big customer base that is going to want to buy that water. So there would be a pretty vigorous space economy that would be set up. So asteroid mining for consumption by Earth orbiting satellites and for space exploration by humans, it's going to be a very important endeavor. So one of the reasons why Osiris-Rex is there is also to identify it as a source of resources for mining. And the fourth main justification is that we may send astronauts to asteroids relatively soon. And if we're going to go to the surface of Mars, chances are we're going to stop in the Martian moons, which are captured asteroids. So understanding asteroids and operating, human missions to asteroids is likely to happen before we get to the surface of Mars. And therefore, by studying Bennu, we're also studying the type of environments that humans will encounter once they get to asteroids.
That's incredible. I mean, I'm just trying to imagine a future like that where I keep thinking as you're talking, I keep thinking of The Expanse, I don't know if you've seen it or not, but it's
I must be the only person left in the US that has
no
not seen
kidding.
that series. Yes.
Well, imagine a world, it's kind of exactly what you just described, this world where mining the resources of the solar system has just become a way of life, and the technology's there. So yeah, once you get some free time, you're pretty busy. You're probably not binge watching Netflix and Amazon Prime, but eventually I recommend it, and you could give us an idea of how accurate it was to real life.
I have to confess, I'm somewhat provincial. I'm making my way through Star Trek reruns and Battlestar Galactica.
Oh, nice. Well, I highly recommend the new Star Trek Discovery. My wife and I just finished it. We loved it.
Okay.
Well, I mean, this is an incredible feat, right? We've gotten to the point with our science, our physics, that we can now land spacecraft on orbiting objects. And this is NASA's first attempt, but this has happened before, right?
That is
JAXA
right.
has done
Yes.
it, what, twice?
The Japanese Space Agency has successfully gone to asteroid Itokawa and brought back samples. They were the first ones to do it, and they beat NASA, the European Space Agency, and the Russians to doing that. And now they've done it again. Their mission Hayabusa 2 and went to asteroid Ryugu, which is about twice the diameter of Bennu, but almost the same shape. And they sampled twice. My hats off to the Japanese Space Agency. They went there, they sampled once, and then they shot a projectile onto the surface of the asteroid, created a crater, and sampled some of the material from that crater, and are bringing back at least samples from at least 2 sites that they were able to capture. They are on the way back to Earth. They'll get back in December of this year. And JAXA and NASA have an agreement where we're going to share 10% of the sample that each mission brings back. So the Japanese are going to give NASA 10% of the sample from Ryugu, and Osiris-Rex is going to give the Japanese Space Agency 10% of the sample from Bennu. So that's great because we get to explore 2 different asteroids and bring back their samples to Earth and understand the materials from both. And they're not the same. They're both primitive asteroids, but they don't look the same. There's certain very interesting differences. For example, Bennu has got a lot more hydration on the surface of its minerals than Ryugu, and there are other things. So, and this picture, by the way, I like to point out, was before we got to either asteroid. This was about 2 years ago. And we were hoping that the surfaces of these asteroids would have large, smooth areas filled with dusty material that would be easy to go down to the surface safely and sample them. But what we got was not exactly that. So whenever you want to continue, I'll go.
Oh, excellent. Yeah, no, well, and that kind of is a great segue into the instruments on board Osiris-Rex. So, many of you that are watching, Osiris, that sounds familiar, right? Well, that's the ancient Egyptian god that was the ancient life giver. And so the coolest part about this spacecraft is its name is kind of somewhat of an acronym of of its mission profile. And so Osiris is this ancient Egyptian god, the ancient life giver, and Osiris-Rex kind of wants to uncover kind of the ancient mysteries of life's origins. So I figured we could take a second and talk a little bit about the name Osiris-Rex, and then talk about some of the instruments on board. So I guess let's hit the name first. So O stands for origins, right?
Correct. And so that means we would like to understand the origin of the solar system and of the planets, and asteroids like Bennu contain the most information about that, including these organic molecules that are not present in they're not present in any other type of asteroid. So, so origins for the O, S, it stands for
Spectral
secure,
interpretation. Yeah.
sorry, spectrum interpretation, and which is we're going to, and we have determined the composition of the asteroid throughout, and that's the S and I. The R stands for I'm blanking out.
Resource identification.
Resource identification, and that's what I was talking about earlier. That Osiris-Rex can identify potential mining resources on Bennu, and we did, right?
Right.
Security is for the last S, and that's because Bennu is a potentially hazardous asteroid, so we want to make sure we can characterize it in enough detail that we can follow it, and if it becomes a threat to Earth, we can deflect it, deflect the impact. And REX, so the original proposal was Osiris, and that proposal made it to phase A, but it never made it to phase B in the program that it was competing for. They resubmitted the proposal for a different program, in this case, the New Frontiers, and it was, they added the REX, which stands for Regolith Explorer. So not only were we gonna do all these different tasks that stand for Osiris, but we're also gonna image and interact with the regolith, disturb it a little bit when we take the sample, and characterize it before and after the sampling maneuver. So that's what the Rex stood for, and I guess it was the charm that the proposal had been submitted in some way or another twice. This was the third time, and we won, and we got funded. The spacecraft has the TAGSAM, which is the instrumentation that will select, will collect the sample, and TAGSAM and the engineers that built it are extremely proud of it. It's very sophisticated instrument where it has the gas that will flow through the head to collect the dust, and it also has the ability to compress a string that is in it, a spring, I'm sorry, that is in it, that as the spacecraft comes down to the surface, the spring that is within this arm will be compressed and will push the spacecraft away from Bennu after the sampling is carried out. So the head of the spacecraft, the sampling mechanism, so the spacecraft itself with this sampling mechanism will touch the surface for 5 seconds. During those 5 seconds, the spring will be compressed and the spacecraft will be pushed away from the asteroid. You may ask why, and the answer is we don't want to shoot our, or be firing any of our thrusters that close to the surface, because doing that could kick up enough dust that will blind all of our cameras, and then we'll be flying blind and may not make it back to Earth. So we purposely designed this spacecraft so that it would compress the spring and push the spacecraft away. That has an element of danger, which is when that happens, it's going to be bouncing back in a direction that we don't know, because it depends on exactly what type of terrain the sample head is hitting. But it allows the spacecraft to not be firing its thrusters at the surface. Once it bounces back and it's at a certain distance from the asteroid, it will look at the stars, look at the asteroids, determine where it is, and fire its thrusters away from the asteroid so that it can perform this maneuver that will tell the spacecraft, or tell us, how much sample we've actually collected. And so that's TAGSAM. OVIRS is the Osiris-Rex visible and infrared spectrometer. OTES is the thermal infrared spectrometer, which was built by, OVIRS was built by Goddard. OTES was built by Arizona State University. All of the science cameras on Osiris-Rex were built at the University of Arizona. So we have Polycam, MapCam, and SamCam. And then we have Rexes, which is an X-ray instrument, which is a student instrument that was built by students at Massachusetts Institute of Technology. And then OLA is a laser altimeter that was built by Canadian colleagues and provided to Osiris-Rex by the Canadian Space Agency. And it was a hugely useful instrument to have on board. Shall we continue?
Yeah, absolutely. I wanted to kind of give our audience kind of a view of what this spacecraft actually looks like as they were finishing up the preparation before they put it into the fairings of the rocket. But we're looking at what, a length of about 20 feet, a width of maybe 8 feet, height about 10 feet. So you had mentioned earlier maybe the size of a minivan?
Minivan, right. And you have the antenna for communication with Earth and the solar panels and the instruments that are all facing, will be facing towards the asteroid. Even during the maneuver, that's one of the things that we're excited about. There were 2 rehearsals of this maneuver, one in August and one in April. And those 2 rehearsals have provided us with such wonderful information that have allowed us to fine-tune the process, and also with images and spectra that are at higher and higher spatial resolution, so we can see smaller and smaller things as we're approaching. So we're very excited with these images for scientific purposes, but also because they reassure us that we selected the best possible site to pick up our sample. We suspected that this would be the area that would have more fine material than anywhere else on Bennu. But as I mentioned before, well, let's move on to some.
Oh, sure.
Of Bennu.
Well, yeah, so we've talked about the launch a little bit. We've touched on Bennu, and we're going to go into a lot more detail. We've looked at the instruments now that are on Osiris-Rex. So once Osiris-Rex is making its way away from Earth to meet up in the same orbit as Bennu, the scientists took this amazing photograph. And this picture, to me, is phenomenal from an astronomy standpoint, from one of the things that we spend a lot of time doing is educating the youth, children that are coming to the planetarium, trying to help them understand the scale of the solar system. And that's hard to do with our minds. We can't wrap our minds around the scale of the solar system, let alone the galaxy, let alone the universe. This photo, can you talk a little bit about how this came to be? We're looking at the Earth and the Moon from Osiris-Rex.
On the lower right is the Earth, and on the upper left is the Moon. And what Osiris-Rex did is that we traded an extra year of cruise time, in other words, of time on our way to the asteroid, in order to save a lot of money on having to use a 3rd stage for the spacecraft. So instead of needing an extra rocket to send us towards Bennu, we used the Earth as a gravity assist, so we could change the inclination of the orbit and meet up with Bennu. And so we encountered the Earth a year after launch, and we used that encounter with the Earth-Moon system to calibrate a lot of our instruments. So, for example, our 3 cameras, our spectrographs, needed to look at things that we had already previous knowledge of, like the Moon and the Earth, so that we would be able to calibrate our instruments, because once you launch something and it goes through the radiation belt of the Earth, that radiation can change the characteristics of your camera and of your spectrograph. So we wanted to calibrate them, and they provided great calibration targets for us to understand how well our instruments were doing, how sensitive they were, how the different colors were being registered. So this provided that opportunity, and we also carried out a little bit of science. We looked for any possible small asteroids in the Earth's Lagrangian points where there might have been some material that was captured. We didn't discover any, but again, we were able to see how deep our cameras could observe by observing fainter and fainter stars. So this is great to be able to swing by Earth. And then a year later, we got to Bennu, which was in late 2018.
Yeah, just a wonderful image. To me, this is right up there with the pale blue dot. I love it. It
Wow,
belongs in a
thank you.
frame.
I will tell the head of the camera probably on Monday that you said that. He will
Oh,
be,
absolutely.
yeah,
Yep,
his
absolutely.
name is Bashar Risk.
Oh, excellent. Well, so a lot of times we get asked, the size of this asteroid, and asteroids, as we know, we've got every size in the book. So this kind of gives our audience an idea of the scale. Now, it's not nowhere near the size of something like Vesta, but
Yeah, Vesta is the second largest asteroid. The largest is Ceres.
right.
Ceres is 1,000 kilometers in diameter. Vesta is about a little over 500. Bennu is 510 meters. So 500, basically 5 blocks across. And which is a little bit bigger than the Empire State Building and a little bit bigger than the Eiffel Tower. Mon Dieu! Anyway.
Absolutely.
So, but yes, and remember, Ryugu is got about twice that diameter, 8 times the volume. We were both looking, and both the Hayabusa 2 and the Osiris-Rex mission went to primitive asteroids. And we had the great coincidence that both their mission and our mission were operating at the asteroids simultaneously. Different asteroids, but we were able to compare notes and share experiences. Especially, they were kind enough to send us the data on how their sampling maneuvers went. And we've applied that to our plans, and that has helped us gain more confidence that our sampling will be successful in the next 18 days.
I love that there is that collaboration that we're all working together for the same goals of science.
Yes,
Yep. So we're getting closer and closer now to Bennu. We've traveled. We're in orbit around this body that you had mentioned. We're hoping for a nice smooth surface, but not quite what you found.
right. So the original plan was for Bennu to hopefully have some smooth, dusty areas like we had seen on asteroid Itokawa, which is a little bit bigger, but not that different in size. And we found that Bennu, until we saw these images, the navigation team, which is a very competent team, I will tell you more about them later. The navigation team said, the spacecraft has been designed and we are navigating it in a way that we need about 150 feet across of smooth terrain without rocks, so we can safely sit down for those 5 seconds and bounce off and pick up the sample. And as soon as we saw these images, we said, no, there is no place that is 150 feet across and has no rocks. And so the navigation team came back to the imaging team, which I'm a part of, and said, well, our spacecraft is navigating so well that we can put it down in half of that diameter, 75 feet. And we said, bah, no such place. And he said, how big of an area that is smooth without rocks can you give us? And we said, well, maybe 30 feet or less, and there will be some rocks in there. And they said, wow, we gotta change our approach. And instead of their original plan, they had to change to a system called natural feature tracking, where the spacecraft goes and maps the potential areas where we're going to be sitting down or to touch and go. And then the spacecraft makes decisions in real time as it looks and says, okay, this rock is this rock, that rock is that rock. That means I am coming down at this speed, and the area where I want to go is over there. So it's got some autonomy, because the communication, basically it's too far from Earth for us to be controlling in real time. So we had to program the spacecraft and then let it go and have it make its own decisions and make corrections that it comes down to the sample side, which we will be seeing in some future images. But I wanted to make a little comment here. Most of what we expected of Bennu turned out to be right. Its size, its rotation rate, and its orbit, all these things. But there were a couple of things that we were surprised about. Number one was how rocky it is. And number two is that Bennu is actually ejecting particles into space with a mechanism that, with a process that we still don't know what it is. And there's been a number of papers published on this already, and it's fascinating. So Bennu is an active asteroid. Somehow the surface is kicking up dust into space. And so we don't understand how, but one of our first reactions was, will those particles be a threat to the spacecraft? We ruled that out very quickly, and then we became very interested in studying them. So we've been studying them. So the two main surprises were how rocky it was and that it was active.
Wow, just fantastic. And these images just show that detail. And we get even closer now here. So now we're going to go and really, how far away would you say for an image like this to get this type of a picture?
The spacecraft was about 100 meters above the surface at this time.
Wow.
And yeah, and look at how rough that terrain is, right? The imaging team and the entire team was hoping for smooth beach-like areas without rocks with 150 feet diameter. No, and here in the upper right, you see that's the Nightingale site, and this is where we're going in another 18 days. And you can see that the diameter of this crater is a little less than 30 feet across, and it's got some areas and rocks that we need to avoid. And so, and yeah, so this is a very rough surface, which is a puzzle because we know that asteroids like this have their rocks constantly break down into smaller pieces, some of which are getting lofted into space by a mechanism that we still don't understand. So we expected some areas where this dust would accumulate to be smooth. And we don't know where that dust is going. Some of it is going into space. Some of it may be going below the rocks somehow. But yeah, it's a puzzle. It's exciting. And it's a little bit unsettling that we have to go in there. Like here's the Nightingale site, and on the upper right, and you see a very large rock on the upper right part of that crater, and we informally call that Mount Doom.
Mount Doom. Nice.
Anyway,
Appropriate. Wow.
shall we move on?
Yeah, absolutely. So when we spoke just recently, you kind of talked about some new discovery, right? So
Yeah.
This is pretty fantastic, and this is hot off the press.
It is. It got published on Monday of last week in Nature Astronomy. And the first author is Daniela Della Justina. The first two authors, Daniela Della Justina and Hannah Kaplan. And they are two very active and remarkable members of the imaging and spectroscopy teams, respectively. And they discovered these bright objects on the surface of Bennu. Most of the surface of Bennu is very dark. It reflects only 4.5% of the sunlight that falls on it. And just to give you an idea, the darkest black than the human eye can see is about 8%. Below 8%, the human eye does not distinguish any darker. Well, Bennu is reflecting about half of that light. And so the great majority of the surface reflects only 4.5% of the sunlight. But we found these boulders, these rocks, these objects that reflected many times more light than their surroundings. And then when we looked at them with the MapCam colors, MapCam instrument on Osiris-Rex has 4 filters, and we were able to use those to determine the colors of these things. We noticed that in the near infrared, they always were reflecting less light. And that was indicative of the possibility of silicates, a common mineral. And so we used the spectrograph and the spectral analysis working group where Hannah Kaplan is a member on, they came up with these very detailed spectra of these rocks. And they said, my God, this is not just a silicate, this is pyroxene, which you do not expect on a primitive asteroid like this. And we continued to think about this, and we said, wow, so that has to come from another asteroid. And let's look at it in more detail. And it turns out that those rocks are pyroxene, which is a type of lava that comes from the most distinctive asteroid in the asteroid belt, which is asteroid 4 Vesta. Vesta is an object that melted, differentiated, the iron in it went to the core, just like on Earth, and then the silicates, the rock-forming minerals, floated above that iron core and eventually solidified. And the surface is made mostly of pyroxene, which is the lightest of the silicates that you expect in objects of this composition. So a chunk of Vesta ended up hitting the parent object that Bennu came from, because Bennu is a small asteroid that came from the disruption of a larger object. So a chunk of Vesta hit the parent of Bennu, maybe broke it up into many pieces, and some of the pieces of Vesta survived in Bennu, which is fascinating because until now, most theorists thought that the projectiles that hit another asteroid are vaporized and we would never recognize them. And here they are. So I was ecstatic when this was discovered. I'm a co-author on this paper, and I've been following its development. This is amazing. We not only have a piece of another asteroid on Bennu, but we have a piece of a remarkable asteroid, which seems to be, actually Vesta is, we think, is the only intact asteroid that differentiated and did not get broken down into many smaller pieces. Vesta has two big craters, but most of the surface is pretty much its original volcanic surface. So we're fascinating that Osiris-Rex might bring us samples not just of Bennu, but possibly of other asteroids like Vesta. So we're very excited about this. And you're gonna have to stop me, maybe shut down my computer if you don't want me to talk all night about this.
No, it's so fantastic. I mean, I think everyone knew that this mission was going to, bring back new discoveries, but it's things like this that rewrite science textbooks,
Yes. Yes.
So just incredible.
We cannot wait for those samples to see if we can get pieces of Vesta in there. So we would have a sample return mission to not just one asteroid, but 3: Bennu, Ryugu, and Vesta. Ryugu because the Japanese went to it and are going to share samples with us, and Vesta because pieces of Vesta are on Bennu. 3 for the price of 1.
There you go.
No, only this week. Buy quickly, and we'll include Ginzu knives with it.
There you go. 3 for the price of 1. Okay, well, excellent. So as we continue to move on, some of the other, discoveries that, the scientists were looking for were, temperature fluctuations, infrared. We've got a spectrometer on board. Talk a little bit about how the importance of understanding, the sun's activity in affecting an asteroid.
Yes, what we have here are at the top the temperature on Bennu, and the temperature is highest at the equator. Bennu's axis is essentially perpendicular to its orbit, so it's hottest at the equator and it's cooler towards the poles. And that heating of the surface of Bennu is making the afternoon side of Bennu re-radiate that infrared, that light in the form of infrared radiation of heat. That gives Bennu a little bit of a push in a specific direction that's making it spiral slowly down towards the sun, and that's called the Yarkovsky effect. And this is the effect that could make Bennu change its orbit and threaten Earth in another 160 years. So that was one of the goals, was to measure the temperature and temperature variations. So these 3 images illustrate different aspects of this. And the other thing that I wanted to point out is that Bennu goes from really hot at noon to way below freezing at midnight back to really hot at noon every 4.3 hours. So, Bennu does not have an atmosphere to moderate those temperature excursions. So the rocks on Bennu are getting heated and cooled, and we know that that's a formula for basically breaking down of the rock into smaller pieces. So that's one of the reasons why we expected a lot of fine dust on Bennu, and we don't seem to see it. So this is fascinating. The other thing that we discovered is that, for example, if you were to go to the beach at night and there's a big chunk of concrete somewhere on the beach, and you sit on that concrete right after sunset, that concrete is still warm because that concrete is still radiating away the heat that it received during the day. But the sand is actually rather cool because it cools rather quickly, it radiates very effectively, and it can heat up fast and cool down fast. So that we know from our experience of going to the beach that either that the big rocks heat up more slowly and cool down more slowly than the sand. What we found on Bennu surprised us because the biggest rock on Bennu, which we would have expected to heat up more slowly and cool down more slowly, is actually the single feature on Bennu that heats up faster and cools down faster. So we suspect that that rock is very porous, so it's behaving like loose sand. Mm-hmm. And the fact that the rest of the surface of Bennu is rocky and not sandy gives us the opposite of what we would have expected, right? So even Bennu is acting the opposite of what we find on a nice summer evening going to the beach, which is the rocks will be warm and the sand will be cool.
Well, again, just more fantastic discoveries. So we are now, getting down to the countdown, right? We are just, like you said, 18 days away. The selection of the sample site was obviously critical. You talked about how, the spacecraft needed a right amount of space to do this. So kind of talk a little bit how, really how it was narrowed down to the site that was chosen for the 20th.
Sure. We went from about 40 original possible areas to 16 to 8 to 4, and now we have 2. So our primary target is Nightingale, the first one here. Our backup is Kingfisher and Osprey. And I'm sorry, our backup is Osprey. Kingfisher and Sandpiper have essentially been ruled out. So Nightingale and Osprey are primary and backup. And we believe we're going to be successful on our first attempt, but if we're not, we will have disturbed the surface on Nightingale enough that we would want to go back to Osprey and get a pristine surface for our sample. And these were selected by looking at the ease with which we would be able to pick up the sample and the ease with which we could navigate in and out. Nightingale was more challenging for navigating in and out, in part because of all these rocks around it, including Mount Doom. So Osprey was easier to navigate in and out of, but we decided to go with Nightingale first because the material on the surface of that crater is believed to be much looser, and we will be able to pick up a much bigger sample if we go to Nightingale. And I'm hoping that that will be the case.
Great, great. Now, when we actually go and do the sample, as you mentioned, there were 2 rehearsals that happened. What kind of real-time information is coming back? I mean, it's not like Mars where we're waiting for long periods of time, no 7 minutes of terror really, but how does the communication work quickly to understand where we're at and how successful?
The spacecraft will be autonomous, as I mentioned earlier, and we will be getting the data, and it will be essentially released to the public immediately in terms of imaging and success of the sampling maneuver. And a few hours later, maybe a few days later, we will have measured how much mass we picked up in the sample head, and we will decide whether we need to go back down and get some more, or we're going to put that sample head into the capsule. And wait until the two orbits align, which is going to be in early 2021, and head back to Earth.
Oh, fantastic. Well, what I did was the Osiris-Rex team and NASA put out a promotional video in preparation. So I'm just going to kind of let that play in the background. But, you know, we are very close to, you know, watching this happen. What happens now between over the next 18 days? The site's been selected, the instruments are ready to go.
Now,
What,
yes.
yeah, what is the team kind of focused on over this last critical period of time?
Well, the navigation team has gone through. Oh, by the way, one of the things that you saw there was an illustration of what it would be like to bring down this minivan with this long mechanical arm
With all that activity around it.
Yeah, into a parking lot where there are a bunch of cars in the spots right around where you want to park for 5 seconds your spacecraft without touching any other part of the surface. So I like that, because that illustrates how difficult it is to navigate and come down and park for 5 seconds in a parking lot that is got cars all around you, you know, millions of miles away, right? And so here you see some of these images. So one of the things that we're doing is that we're counting and measuring the sizes of rocks right in the area where the sampling maneuver will occur. And once the sample has been obtained and collected and put into the capsule, we can relax a little bit. Right now we're not, but once that's done, we can relax a little bit and dedicate ourselves to analyzing the images in terms of the science that we can get out of having studied this asteroid for 2 years. So there you're seeing the maneuver of the Osiris-Rex that was in orbit around the asteroid, coming in and doing the sampling maneuver, which is like a checkpoint, and the sample head on the left, where once we touch the surface for those 5 seconds, nitrogen gas will be released, and that will fluidize the dust and bring it into the container. And once we've done that, we will bounce off of the surface and move away from Osiris-Rex. I mean, from Bennu and Osiris-Rex, will eventually head back to Earth.
Yeah, absolutely incredible. So you mentioned when we saw earlier the giant solar array that is on the spacecraft, and that's essentially powering the electronics on board. But in order to make these maneuvers for the touchdown, there's still a kind of a reserve of
thrusters, yes.
Thrusters to make those maneuvers.
Yes, and so we have the main engine in Osiris-Rex is a solar electric propulsion, where it accelerates xenon atoms that have been ionized and accelerated in the direction opposite to where you want to go. And that allows tremendous ability to change orbit, to navigate in different directions. But it's a small thrust over a long period of time. In order to make the quick changes in direction that we need when we're near the surface, those thrusters that are around the spacecraft for quick changes in attitude and direction will be used. But again, we will not use them at the surface because we don't want to kick up enough dust that we could be blinding our cameras. Mm-hmm. So we will touch, compress that spring, push off, and then once we know which direction we're going, navigate away.
Oh, incredible. And then once we have a successful collection, do we immediately head back to Earth?
No, we have to wait until the orbit of Bennu and the orbit of Earth line up, so we don't have to change the inclination again. And once that happens, we'll be heading back to Earth on that plane, and arriving in August of 2023.
Okay, fantastic.
Yeah, I will have a little bit more time to dedicate to analyzing the images between now and 2023, but I can't wait to see that sample. I'm excited to see what the sample team will do once that sample gets here and all the results that we're going to get.
Yes. Yeah, it's going to be just an exciting time. So, you know, we've got a lot of anticipation building. We've got so many people that are interested in this mission, and I just can't thank you enough for spending an hour with us to go over this detail. And I really hope that you know, just very similar to when Bob and Doug went up in the SpaceX rocket earlier this year, that we see that same type of media presence. I'm sure your request for news is going to probably go through the roof over the next 10 days or so, I imagine.
Yes, and we're looking forward to that, and that's part of our job, right? It's our job and our pleasure to talk to the press and to talk to the public. And I just wanted to tell you that while I've been talking to you, I've been privileged to a beautiful Arizona sunset, and if I may show it to you.
Oh,
I'll
yes, I'd love to see it.
Peek out the window. I'm not sure if you tell me if Justin, if you can see the Catalina Mountains and
Oh, yeah, it's beautiful.
And those are saguaro cacti over there. So I've had the privilege of working here with this view out of my office, and it's getting a little bit dark now. It's, you know, it's 3 hours earlier than Florida. It's just been a great privilege to work with this team here in Arizona.
That's great. Now, has, you know, in the world that we're living in right now, obviously, you know, the team did not anticipate a pandemic breaking out during this mission. How has that affected the daily work life for the team?
We work mostly remotely, although that wasn't my plan when I came here in late June. But there are still people that go into the building for essential duties. There are certain computers that have to be used there. There are certain instrumentation that has to be accessed from there. The team continues to meet quite regularly, several times a week on Zoom. So there's been many advantages to being here. I wish we were meeting more in person than we do, but not at the risk of our health.
Absolutely. Well, great. Is there any kind of final thoughts you'd like to share with us on, on this mission, or any new science that this mission has kind of, excited or shown that we need to continue to pursue these
many
types of
things.
avenues?
Yes, I mean, I've only just touched on some of our discoveries, and there are going to be several papers following up on the discovery of the chunks of asteroid Vesta on Bennu, and there's a lot of theory being done on how is it that these guys survive. And so in a few months, I may be able to tell you more about what we've learned about how much sample we have in that sample head, about other discoveries that we've been doing. So if you wanted me to come back, I'll be glad to in a few months and tell you some more about what we're doing, and hopefully when Osiris-Rex is already on its way back to Earth.
Oh, that would be incredible. Thank you very much. We will definitely take you up on that offer.
And my other comment is, those of you who can go to the beach, please go and enjoy it. I love the mountains here, but I miss the beach.
Well, it'll be there when you get back. So focus on your work. You're doing incredible things. I mean, the work that you're doing, it literally affects the future of humanity. So thank you for the work that you and the team are doing. And I wish you the utmost success on the 20th. And everyone, tune in that day, whether it's online or keep an eye on the news. And we're excited to see the developments as they happen. So I'm going to go ahead and say goodbye. I'm going to stop the recording. You and I can continue to chat, and I'm going to thank you everyone for tuning in. This will be live on our YouTube channel. You can watch it live or watch it on a recording. So I'm going to hit